on physical downlink shared channel. And Professor Abhay Kumar sir received the PhD degree from the Department of Electrical Engineering, IIT Kanpur in 2017. After PhD, Abhay Kumar sir has worked at Samsung R&D Institute, Bangalore as a senior lead engineer, where he primarily worked for 3GPP release 14 feature developments. Later, he worked as Redisys India Private Limited, Bangalore as a lead software architect and were involved in the physical uplink shared channel algorithm development for 5G base stations. Currently, he serves as the assistant professor in the Department of Electronics and Communication Engineering, IIT ROORKEE. He is also a senior member of IEEE and the vice chair of the IEEE Communication Society, the UP section chapter. His research interests are in the realizing massive MIMO system for next generation wireless technologies and in the applications of deep learning for wireless communication systems.
Good morning.
In the related domain, he has published more than 25 articles and have more than 25 global and Indian patents so far. He is the recipient of the Mathematical Research Award for the 6G use, SERB Startup Research Grants, DST Inspire Faculty Program, TCH Research Fellowship, and the Vice Chancellor Gold Medal for Outstanding Performance in his bachelor's degree. He has also received Samsung Citizenship Award for the contribution to 3GPP Release 14 features. There is a long list of his contribution and achievement, and this short introduction is not justified. Without taking much further time, I call Professor Abhay Kumar sir to take over the session. Sri Abhay Kumar sir. Sir, I am making you the presenter.
Yeah. Thank you, Sanjay ji, for the kind introduction. Let me share my screen. I think you need to make me presenter.
Yes. Sir, I have made you the presenter. Go ahead.
Yeah. Thank you.
Yes.
So, is my screen visible?
So the screen is visible. Anyone can tell?
Yes, sir. Yes, sir. Visible.
Yes.
Yes, it is visible.
Yes. Thank you, everyone. So,
for me, it is visible. Any participant can also. It's over to you, sir.
So, thank you, Sanjay ji, and welcome everyone. So, this talk is about to understand the building blocks of 5G physical layer downlink data processing. So I am Abhay Kumar sir. I am an assistant professor at IIT ROORKEE. My research interest primarily lies with the next generation massive MIMO system, which is the ultra large massive MIMO system, cell-free massive MIMO system, distributed massive MIMO system, and beyond 5G systems, and also in the applications of AI ML for wireless. I have 12 plus years of experience in the field of 5G system. Previously, I worked at Samsung R&D Institute, Bangalore, and Redisys India Private Limited for the 5G development activities. I have 25 plus IEEE journals and conferences and 15 plus national and global patents on the related technology. So let me move. So this talk, we will cover in 3 parts. So part 1, primarily we will be focusing on the basic introduction of 5G, the different use cases, performance indicator, and information theoretic motivation, the frame structure of 5G, and the information flow, how the data or the other types of information that flows through different channels. So this will be covered in the part 1. In the next part, we'll be focusing on the physical downlink shared channel, which is the channel responsible for carrying the data signal. And it also has two parts. In the second part, we'll be covering the transport channel processing, which enables the error correction and error detection mechanism in the whole data. Part 3 will be covering on the physical downlink shared channel, continuing the same, but primarily focusing on the physical part of it, where scrambling, modulation, layer mapping, how these things are done in the 5G downlink data processing, that will be covered. Lastly, we will also briefly cover a MATLAB implementation. So this is going to be a long talk, and I hope you'll stay with me in this throughout this 3-hour session. And so let's, and lastly, we will summarize this talk. So let's move with the very first thing that you should be aware. What are the key differences if you want to learn all these things? So so there are 3GPP. 3GPP has different series of standards. So 38 series basically primarily related with the 5G standard. Even inside the 38 series, there are sub series like 0.2xx starting from 0.211 to 0.214. They are primarily explaining all the physical layer part of the 5G standard. And if you do not want to invest time, you can also invest time on like there is a website called ShareTech Note. Many of the figures and diagrams I have taken from there, not all. So, and if you want to just briefly understand, you can also visit this website and try to get some idea about the details of the 5G standard. So let me start this talk with a very pertinent question. We might be aware of also why we needed 5G, because this 5G discussion started somewhere early 2010. And that point of time, it was envisioned that because the use of communication technologies are growing at a very rapid pace, and it's not only human-to-human interaction, because machines are also coming into the picture, where machines can interact with another machine and take an information, take a collective decision, or like for an IoT use case or machine-machine type use case. So we need a next generation of wireless communication. And that is the one primary reason people have started towards the 5G. The second is that till before 5G, it is largely about getting higher data rate. But 5G is not only about the getting faster, it brought new functionalities and applications which has very high social and economical value. So let me begin this talk with one short video. Let's think, give me a moment. I think I need to. Yeah.
Hi guys. Okay, good. So today we're going to feel the difference between 4G and 5G.
Good.
Do you see everything?
Yeah.
Let's find out, bro.
Now that's 4G. Now let's try 5G.
Easy.
Well done, bro.
Thank you.
That's 5G.
Okay.
You're going to feel the difference between 4G and 5G. We'll start with 5G. So put this on. Yep, good. Marco, now it's 4G. Good.
No.
Oh, Linus, can I switch?
Yeah, of course.
No.
Ça, c'est des football.
Yeah, so I hope you have enjoyed this video. So this video is not a new video. This was shot somewhere around 2017 by Ericsson, and it is available on YouTube also. So you might have noticed a very important aspect here that is being discussed, like that is latency. Two sets of footballers came. They have tried different things, but you might have noticed that because of the latency, it is not about the data rate, but it is about the latency which plays important role here, and that is all about 5G. So it's not only about the data rate, but there are other certain key performance indicators that also has to be met to call it a real 5G. So let me move. So based on this, different use cases has been envisioned. So there are primarily three verticals: enhanced mobile broadband, ultra reliable low latency communication, and massive machine time communication. So if you put this in a vertex of a triangle, so there are a lot of applications which can play around all these different vertices. Something like a color spectrum. You have red, green, and blue, and you can create so many different colors out of it. Similarly, here also you have these three primarily focused use cases of verticals. And if you mix and match all these different combinations, you can have different use cases. For example, self-driving car that is very focused towards an ultra-reliable, low-latency communication. Whereas somewhere augmented reality, it also requires an enhanced mobile broadband support as well as an ultra-reliable, low-latency communication. So it's kind of mix and match. We can create a lot of different application and features. So, and few of the key application features are highlighted here. You can talk about e-health, where a person, a doctor, let's say from Delhi, he can operate somewhere in, let's say, Manipur, Mizoram, or any remote part of, let's say, Lakshadweep, without physically visiting there, and he can operate from an urban place. Similarly, we have connected house, where there are a lot of gadgets around houses. They can communicate with each other and take an informative decision. For example, we have thermostat in our houses, and we have, let's say, smoke detector. Thermostat states measure the rise of the temperature. Smoke detector measures if there is some smoke happen. Sometimes if a person is smoking, probably the temperature has not risen up enough. But smoke detector will give you a false alarm. But if you mix these two, probably you will get a better informed decision. So that is about the connected houses. Then we have entertainment, smart car, that is also important and an interesting application. Yes. So the idea of secure transport is that vehicle will be able to communicate with outside world and become more secure. So imagine you can think of a doctor is driving on a motorway on a rainy day, and it is behind a truck. So if the truck has a limited visibility, if you put a camera somewhere or a screen behind it, or let's say the person, the car which is moving back of this has the idea what is going upway, so it can take a more informed decision while crossing the or taking uh, crossing the vehicle. For example, I'm again have one small video. Probably that will give you a better idea about how the secure transport works. This is an initiative by the 5G communication automotive research and innovation, where the automotive sector and 5G has bring hands together. And this is again a slightly old video. Once it is being envisioned, people have this. So you can see here there are 1G, 2G, 3G. Similarly, there is a generation of automotive sectors. Now, what is the idea to merge these two together and make a 5G car? Now this will all about different set of, it requires speed, coverage, less latency, V2X, IoT, lot of data, lot of sensors. So, so you can see here in this video, this is self-explanatory. So there is a car coming from sideway to the highway. Now there is a data server which sends there is a car coming up that gives some information to the another car. Now automatically the car slows it down, and it gives a pathway to the other car so that it can merge with the lane. Now you see the another example. Now the vision of this, the car which is backside of the truck is blocked by the truck. Now it wants to cross that truck, overtake that truck. How should it do? So there is a feedback going on, and then it sends that okay, there is a pathway is clear. Now it can take the overtake. Similarly, this is an example when a pedestrian is crossing, and there is an obstacle which has blocked the vision of the driver. But this pedestrian has a mobile phone which anyway connected to the cloud and the network. That gives a vision of to the car or the driver that there is a pedestrian which is coming, crossing the road. Okay, so this is all about like different use cases. Now, how we can support this? So there are certain performance indicators are defined to measure the performance of a network, or you can say the 5G network. Now it displays how effectively a network is serving a user. So in 5G, there are several performance indicators are defined to benchmark the values for setting up a minimum performance requirement. So if you can call a network of 5G if it is able to serve these numbers at least. So I have like you can see there are this table. The first column represents the key performance indicator, which is listed down the indicators like peak data rate, spectral efficiency, energy efficiency, mobility. Now latency has two types of latency, user plane latency and the control plane latency, reliability, connection density, and the battery life. The next two columns basically compares the numbers between 4G and 5G. Now the numbers of 4G are not actual 4G numbers, but it is from the LTE Advanced, which is the advanced version of 4G. So you can see the peak data rate goes or downlink data rate goes from 500 Mbps to 10 Gbps or 1000 Mbps to 20 Gbps, which is 20 times increase in terms of a peak data rate. Now, if you think about spectral efficiency, that number also gone from 0.7 to 2.25. Why this is a range? Because spectral efficiency is defined for different use cases, like rural scenario. The targeted spectral efficiency is different. For urban scenario, the targeted spectral efficiency is different. So this is within the range. This range also has been scaled up by a factor of 3 roughly. Similarly, you have energy efficiency. Energy efficiency. There was no notion of energy efficiency in 4G or 4G LTE Advanced. The idea here is to maximize the energy efficiency. Then mobility, the earlier number was the maximum support was up to 350 km per hour. Now the maximum support has been scaled up to 500 km per hour. Latency, which is 5 millisecond roughly, now has been scaled down to 0.5 millisecond of the order. Reliability, there was no number of reliability. Now that number is 99.999%, which means if you are sending 10⁵ number of bits, only one bit can go into the error, not more than that. Connection density also has been scaled up. Like earlier, the targeted number was to support 60,000 device in a square kilometer area. Now we have 1 million device per square kilometer. The battery life for the IoT use cases has been targeted from 10 years to 15 years. So you can see here different use cases requires different performance indicator. For example, the latency and reliability are related with URLLC, spectral efficiency in a data rate they are with the EMBB use case, and NCT and the battery life they are with the MMTC use case, that is massive machine type communication. So now if you draw these two in a circle, you can see this is a vertex. Every vertex has been scaled up. So the lighter green shade shows the numbers of the 4G LTE Advanced. The darker green shade here shows the numbers of the 5G. So you can see that every vertex, that user experience, the spectral efficiency, mobility, every number has been scaled up. But the question arises here is that how can we achieve these numbers?
Sir,
So
sir, good morning, sir.
Yes,
In the
please.
previous slide, you have mentioned that in the 4G, it's 60,000 devices per square kilometer. But in this figure, if you see, it is 1 lakhs to 10 lakhs. It increased from 1 lakh to 10 lakh. And here you are showing that it's a 60,000 per square kilometer. It should be 1 lakh, I hope.
Okay, let me check. Okay, see, this number, like I have taken these two from two different sources. I think that number is slightly on a logarithmic scale. So that's why this looks very close to 1 lakh 10⁶ number, probably. But this was the actual targeted number. This has been taken from the actual, there was a discussion around INT. So this table was formulated at that point of time. But the idea here is that every number has been scaled up. But the question was that how can we achieve these numbers? So here we'll be focusing on the first goal, that is for EMBB use case. EMBB use case, that how you can enhance the capacity. So the one idea for enhancing the capacity is that, so if you remember the first characterization of the capacity, which is done by Shannon, this basic capacity is scaled by W, which is the bandwidth times log of 1 plus SNR. So the question is ahead with us, how can we increase this capacity? So the answer for this is very simple. So either you increase the bandwidth or you increase the signal power. For example, you can see here, if you increase the SNR, capacity scales linearly. So from 10 dB to 30 dB, so roughly it was around, if you see this number, so if you see this number, somewhere around 15 dB, you are getting 5 bits per second. Now, if you increase to 30 dB, you will get somewhere around 10 bits per second per hertz. Now, this number, so this is one way to achieve it. The other way is that if we can improve the utilization of the spectrum, and that's where massive MIMO comes into the place, or you increase the receive SNR, where the beamforming comes into the place. So in this discussion, we will take the simpler route and try to understand what is that simpler route to increase the bandwidth. We will take, so you might be heard of the 5G recently last year, that there was band auctioning by the government, and a total of 10 bands has been auctioned. Roughly around 72,000 of megahertz of spectrum has been sold out, given to different operators. And this is the list of those auctions, the bands in auction. The question here is that, although we are talking about increasing the band, like you can increase the band and you can definitely get a better data rate, but it's not that straightforward. So why this is not straightforward is that it is because of the inter-symbol interference. There is a phenomena called inter-symbol interference. We will understand how this increasing the bandwidth creates this inter-symbol interference problem. So you see this, let's say you are transmitting a symbol, symbol 1. I see there are a lot of background noise. Request everyone to mute your And kindly mute your mic. Kumarji, please kindly, can you mute your mic? Yes, thank you. Yeah. So there are a lot of yeah. So let's say we are transmitting symbol 1. So this is the, so what will happen? This symbol 1 will be received through multipath. In a wireless medium, whenever you transmit any symbol, it will be received through multiple paths. So we are receiving first copy of the symbol path, symbol 1, let's say through path 1, and we are receiving the second copy or the nth copy, I should say. So this is basically your path 1, and this represents the path L. And because there is these two paths may have different delays, they will not be received at the same time. Similarly, so this duration, the gap between the first copy and the last copy, is called as delay spread. Now, let's say you have transmitted symbol 2. So what will happen? There will be again a symbol 2 will also be received in a similar fashion. And there will be some region which is being overlapped. So if this overlap is significant, it will start creating a problem called inter-symbol interference. So ideally, we expect the symbol time TS to be greater than or significantly greater than the delay spread, which is this overlap duration. So in other words, the signal bandwidth, which is inversely proportional to the symbol time, and the coherence bandwidth, which is inversely proportional to the delay spread, the signal bandwidth should be less than the coherence bandwidth to avoid the inter-symbol interference. Now, if you notice this tau d, which is or the coherence bandwidth, because they have a unique relation, they are environment dependent. We cannot control what is the delay spread, how many number of multipath, that is basically environment dependent. The length is also depends on the environment. So we cannot control the value of tau d and bc. But what we can do, we can control the symbol time and the signal bandwidth. So what should be the symbol time that we can control? So that implies that we must restrict the signal bandwidth to less than the coherence bandwidth to have a no ISI scenario. So if you want a no inter-symbol interference, your signal bandwidth must be lesser than the coherence bandwidth. But if you have put such constraint, you cannot increase your bandwidth beyond a certain point, and that will restrict your achievable data rate. So that expression C B log 1 plus SNR, your B now is restricted by this coherence bandwidth. So even if you're buying so like ultra like large bands and you have a lot of bands available, you may not be able to use it. So what is the solution? The solution here is that okay. So the solution here is that we can delay the transmission of the second symbol. Like you can create some gap, like you don't transmit the second symbol immediately after the first symbol, but that will have their own consequences, because if you're delaying, basically you are not pumping enough data to your system, and that will eventually affect your overall data rate. Or you can employ a complex receiver at the receiver side so that you can minimize this inter-symbol interference, which again increase the cost of the receiver. A better or much simpler way is to use a technique, multi-carrier technique, namely OFDM. Now this allows us to increase the signal bandwidth without causing an inter-symbol interference, and also keeps the receiver complexity low. So I will not go much detail on the OFDM, the technical aspect of the OFDM, but I will briefly discuss what is the basic idea, like how OFDM is so powerful that it is able to handle this ISI or remove this ISI completely. And we don't need any complex receiver. We don't need to delay the transmission. So the basic idea here is that we divide this whole bandwidth. So you have B band, we divide this whole band into N sub bands and use them for concurrent transmissions of n symbols. So you have a larger band, we are dividing into smaller bands, and each band is transmitting an independent symbol. So this is a single carrier system where you have one carrier and it is carrying the data. And in a multi-carrier system, we have B band, which is divided into n sub-bands, and there are n carriers. We call them as a subcarrier. They are carrying n independent data streams. So what it results? It results that each subband will be n times larger. So the symbol time in each subband will be n times larger. Why? Because you are reducing. So earlier your bandwidth was B. Now you are dividing by n bands. So each subband will be B by n. So B by n means symbol time is inversely proportional. So that will increase by n times larger. So let us understand this through one example. So what I'm considering one example here. So consider a 4G system. Why I'm considering 4G system? Because 4G also uses the OFDM, 5G also uses the OFDM. So let's consider a 4G system having a bandwidth of 20 megahertz, and the subcarrier total number of subcarriers is 1200 subcarriers. Now they are operating in an urban scenario of maximum multipath separation of 300 meters. So it means to say that the gap between, let's say this is one path, and the gap between, let's say, another path. So this distance is, let's say, D0, and this, let's say, DL minus 1. So the DL minus 1 minus D0 is 300 meters. Can you find what would be the delay spread in this case? So delay spread is the time gap between the first reception and the last reception. So what do you think would be the delay spread in this case?
1 microsecond.
Yes, absolutely right. So how you have calculated? Can you guide us?
So we have the difference between the two multipaths as 300 meters, and we divided by speed of light in
Distance by
meters.
velocity.
Yes, distance by velocity. So 300 by 3 into 10 raised to power 8, which is the speed of light, which with all electromagnetic waves travel with the speed of light. So this will be, turns out to be 1 microsecond. Now what would be the coherence bandwidth in this case? Coherence bandwidth is 1 upon 2 times of tau d. So if you use this, you will get some number 1 by 2 into 10 raised to power minus 6. So it will be 500 kilohertz. Right? Now, if you see this problem, now your total bandwidth is 20 megahertz, which is the signal bandwidth, and you have coherence bandwidth of only 500 kilohertz. So that simply indicates that coherence bandwidth is smaller than the signal bandwidth, and you will have this problem of inter-symbol interference. Let's calculate what is the symbol time for single carrier transmission. So that will be, you can easily calculate by 1 by B, which is 1 upon 20 megahertz. That will be, turns out to be 50 nanosecond. So 1 by 2, 0.5, 10 is for minus 7. So 5 and 50 nanosecond. Similarly, if you find symbol time for multi-carrier transmission, which is 1 upon B by N. So this will become 1200 . So 1200 into 10 raised to power 6 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised to power minus 7 into 1 by 2 into 10 raised by this 20 megahertz. Now this number will be 1200 times this 50 nanosecond, which will be 60 microsecond. Now you can see in the case of multi-carrier transmission, 1200. Now this number is much greater than the delay spread. If you compare these two numbers, 60 microsecond is much greater than 1 microsecond. So you will have no ISI kind of scenario. So you will have no ISI. But if you compare these two, which is the single carrier transmission, 50 nanosecond is much smaller than 1 microsecond. So you will have intersymbol interference. So by using this notion of OFDM or multi-carrier transmission, we are able to overcome this issue of intersymbol interference. So this diagram basically summarizes these two things. So in the case of single carrier system, you have symbol 1, then we have transmitted symbol 2, then we have transmitted N symbol. So N by B seconds, you are able to transmit N symbol. But in case of multi-carrier transmission, what we are doing, we are parallelly transmitted N symbol over N by B time duration. So you are not increasing any data rate, because in the same duration you are able to transmit same amount of information. But now you are able to utilize the larger bandwidth, which gives you the advantage because now you can pump more data into the system. So this is the precise reason OFDM is being continued from 4G to 5G, and it is one of the key pillars of 4G as well as 5G transmissions. So now we will be briefly discussing the frame structure. I hope you have, probably it has been covered in the previous one of the talks. So each frame, so the frame structure has two parts. One is time, another is frequency. So in terms of time, so each frame which is of order of 1 millisecond, each frame of the order of 10 millisecond, which is further divided into 10 subframe. Now each subframe will be of 1 millisecond. Now each subframe is further divided into some slots. This slot can vary. So it can be 1, 2, 4, 8 or 16. So there are 5 combinations that is allowed. So a subframe can further be divided into smaller units, that is called slot. And this division can be either 1, 2, 4, 8 or 16. It cannot be 5 slots. There cannot be 9 or 10 slots. It will be always 1, 2, 4, 8, 16. Then these slots are further divided into symbols. This is all OFDM symbol. This number can be 12 or 14. So 14 is the normal number. Most of the cases it will be 14. Only if there is an extended cyclic prefix case, this number can be 12. So in our discussion, we'll be assuming this number to be 14 only. Now this is all about the time aspect. Similarly, there is a frequency aspect. So the maximum bandwidth that is allowed in 5G is 400 megahertz. So one band can be of 400 megahertz, which is divided into several subcarriers. Now these subcarriers can range between 15 to 240 kilohertz. So 15, 30, 60, 120 and 240. So these are the different subcarriers spacing that is allowed. Again, 45 kilohertz is not allowed, 90 kilohertz is not allowed, 80 kilohertz is not allowed. So only 15, 30, 60, 120, 240s are allowed. Now, if you combine these two aspects, time and frequency, we can see something, a grid kind of a structure like this. And this grid, yes.
Bit slow, you don't mind bit slow. It is going bit faster, bit slowly.
Okay, fine. Okay, I will try to be slow. So what I mean to say here is that, so there is a frequency, like this part covers the time aspect. and this direction covers your frequency aspect. And each cell here, we call this as a resource element. Now this resource element will carry your modulated symbol. So let's say you have a QPSK data. So this one element will carry that QPSK data. Now this, what this indicates? This indicates that probably, let's say you are using 15 kilohertz. So within this 15 kilohertz subcarrier and this time duration is that symbol number. Symbol number means you have 14 symbols in each slot. So if you are considering like one subframe, which is of 1 millisecond, is divided into one slot. So let's say one slot is of again 1 millisecond, and which is again divided into 14. So this duration is of 1 by 14 millisecond. 1 by 14 millisecond. So this smallest entity here, 1 by 14 millisecond of time, 15 kilohertz of band, that carries a QPSK modulated data. Now, there is a grid. Now, we call 12 subcarriers and 14 OFDM symbol. This unit we call as a resource block. And similarly, there could be so many, like many resource blocks in a system. For example, if you have a 20 megahertz system, it may have 106 number of resource blocks. So this entire grid is called as resource grid, where we map our data. So that is the idea. And we take one column of this grid and we perform the OFDM operation. So each one column of this grid will be your one OFDM symbol. So based on this idea, this is a table that summarizes all different frame structures. So there is something called numerology. So there are 5 numerology, 0, 1, 2. These two are same. Only difference is that the cyclic prefix is one is normal, another is extended. 3 and 4. So there are total 5 combinations. So if you are using numerology 0, your subcarrier spacing will be 15 kilohertz and slots per subframe will be only 1. Whereas if you are using on numerology 4, subcarrier spacing will be 240 and slots per subframe can be 16. So each subframe may have 16 slots. So depending upon this, you can see that what is the symbol duration here? 66.6 microsecond. Whereas in case of numerology 4, one OFDM symbol is only of 4 microsecond, 4.16 microsecond. Similarly, so now these two tables basically summarize the bandwidth. Now, what is like 5? If you think about numerology 0, it supports 5 megahertz to 50 megahertz. All these different combinations. If you are having numerology 4, you can have bandwidth, minimum bandwidth supported is 50 or maximum bandwidth supported is 400 megahertz. These numbers. And these numbers represent how many number of resource block can be there in a resource grid. So resource block is 12 cross 14, 12 subcarriers, 14 OFDM symbols. 32 means you have 32 such resource block that is forming your resource grid. So, so the idea here is to understand that it is a time frequency grid and which carries different types of information.
Excuse me, sir.
Yes.
Sir, can you please go to that second last slide? Can you please once again explain this part?
Okay, just a minute. So what I'm saying here, that there are total 5 different numerology that is supported. So let's say you have chosen numerology 0. So your frame structure is fixed. If you are chosen numerology 3, your frame structure is fixed. Now what is that? This table summarizes that. So if you are, let's say you are selecting frame number numerology 3. like this one. Now it means that your subcarrier spacing must be 120 kilohertz. And so the grid I have created, in that grid, this one subcarrier is of bandwidth 120 kilohertz, right? Similarly, the symbol duration for this will be fixed to 8.33 microsecond. Now, how this number is 8.33 microsecond? For that, you need to understand this particular thing once again. So 10 millisecond is divided into 1 millisecond. Now this 1 millisecond for numerology 3, there will be 8 slots. So it becomes 1 by 8. So each slot will be of duration 1 by 8 millisecond. Now this 1 by 8 millisecond is divided into 14 equal symbols. So it becomes 1 by 8 divided by 14. So which is 1 by 8 into 14. So that many number of, so 1 by 4 into 18, which is I think 1 by 112 millisecond. So that number becomes this 8 microsecond, 8.33 microsecond. So basically you can choose one of these numerology, and based on that your grid size will be defined. That is the idea.
Excuse me, sir.
Yes, please.
Here for the numerology 2 and with the cyclic prefix type of extended, we are saying that OFDM symbols will be 12. Is it because of some pilot signals that have been sent?
Okay. So what it's not, I am saying this is the standard. Whatever I'm covering, this is written in the standard. So if anyone designing a system, they have to choose this number. They have to use this number. First thing. Now, why 12 and why 14? Because now you have more space to have cyclic prefix. Extended means what is the cyclic prefix duration? Cyclic prefix, you know, right? It is like once we transmit an OFDM, we add some additional symbols at each block. There is something called inter-block interference. We have avoided inter-symbol interference, but for 2 consecutive blocks, there is a possibility to have something called inter-block interference. So we add cyclic prefix. Now this number, like in normal cases, like you see this case, this number was 1.17 microsecond. But for extended case, it has been scaled to 4.16 microsecond, so that it can have support more worse environment. Larger delay it can handle. So that is the idea. This extended cyclic prefix case has been introduced.
Thank you, sir.
Yeah, welcome. So okay, so now, so what is the idea? That you have a time frequency grid that will carry different information. So you can see like this is a resource grid. Now, what are different information it can carry? So one is that it can have something called broadcast channel. Broadcast is something which is being broadcasted to all the users in the network. For example, there is something called synchronization signal. So which is being broadcasted for all the users. So if any user switch on your mobile phone, so it has to first synchronize with the network. So in that case, it can use that broadcast information to get sync with the resource grid or the align with the frame boundary. So that is one sort of information. It also has different information like some top level, which numerology you are using, what is the cell ID. All those informations are part of like the broadcast channel. Then there is something called shared channel, which primarily will be dealing in this like talk, which is shared channel is nothing but your data channel. So this grid will also, some part of this grid will have this broadcast channel, some part of this grid will have, let's say, this shared channel, which is actual data. So which is being sent to the user. Then there is something called control channel. Control channel, you can think like, let's say you are sending some sort of a control information. For example, which modulation scheme a receiver should use, or you can think about acknowledgements. Like say you have received back data in the uplink direction. Now you are sending whether you have received it correctly or not. Negative acknowledgement, positive acknowledgement. So there are different types of control channel that also goes through the same grid. There is a synchronization signal and broadcast channel. They goes together. So there are synchronization signal is part of broadcast channel, and then there are some other information also related to beamforming, related to something called master information block that is being transmitted through the broadcast channel, which is a top level information which is required at the UE side to perform the decoding operation. Then there are something called reference signal. Now reference signals are your pilot signals. So there are different types of reference signal. There are reference signal to measure the channel. There are CSIRS. There are sounding reference signal, which is measure again to measure the your pilot signals, the channel. Then there are different types of reference signal, demodulated reference signal. So there are different types of reference signal which are being sent for estimating some sort of information. For example, the channel. Now, once everything you have mapped here, then you will be performing the OFDM operation. So this part basically captures the OFDM operation. So what you will be taking, you will take one column of this grid. Let's say this is the first column. This first column, you'll be performing the endpoint FFT. So let's say you are 20 megahertz, 1200 Ks. So what you will be doing? 20 megahertz, n is let's say 1200. So you will go nearest 2 raised to the power x, so which will be 2048. So you'll be performing 2048 operation here. Endpoint FFT that will be again mapped to parallel to serial multiplexer, and then from this information block, what you will be doing, you will pick some information from the end and you will place it somewhere at the front. That is your addition of cyclic prefix, and that will be transmitted on the air. So this is whole the way the information flows in a downlink direction specifically. So this is a sample frame allocation. You can see here there are different colors. So you can see the first two colors, which is yellow and orange. These two colors represent your PDCCH and PDCCH DMRS. So PDCCH stands for physical downlink control channel. So they are basically control channel, and DMRS is the reference signal related to PDCCH channel. So if you have to decode this PDCCH information, you need to first estimate the channel. You can use this orange color, which is the pilot signals or reference signals, and you find the channel, and then you can demodulate the PDCCH, which is the control information. Similarly, you can see there is some color block boxes here. So this is mix of 4 information: PSS, SSS, PBCH, and PBCH DMRS. So PSS stands for primary synchronization signal. SSS stands for secondary synchronization signal. PBCH stands for physical broadcast channel, and PBCH DMRS stands for physical broadcast channel, the reference signal corresponding to the physical broadcast channel. So now this whole together is your club of broadcast channel and the synchronization signal. We call this as a SS block, synchronization signal block. Now why this is here? So there are various purposes. One purpose is to get the synchronization. So whenever a UE wakes up, it will use these signals to synchronize. So they are broadcast in nature. It goes to and periodic in nature. With some periodicity, it is transmitted always by the base station. Then there are other information. For example, what is the ID of the base station? So that can also be decoded by these PSS and SSS. Then there are PDSCH, which is basically carrying the master information block, which is some top level parameter which is required to know to get some parameters about the communication. So, and then you see this red and light red part. The majority of part is covered by that color. This is your actual data that we are transmitting. So in this, like in the next part, we'll be mostly focusing on how this light red color part is being generated. What is the sequence of operation that is being followed? So let me do a summarization till this point. So what we have learned so far, we understood different use cases, 3 use cases, namely EMBB, URLLC, and MMTC. We have seen the key performance indicator, which is used to measure whether you can support that use case or not. Subsequently, we focus on achieving the data rate number for EMBB use case. So how we can improve the band and get those numbers. So for this, we need to understand the multi-carrier modulation. We get some idea how this OFDM divides a larger band into smaller subband, and that makes the symbol time larger so that it can handle the delay spread or the intersymbol interference. We have also further learned how this OFDM is utilized in the 5G frame structure and different numerology, and how it is carrying this resource grid is used to carry different 5G signals, namely your broadcast channel, which is again master information block and your synchronization signal. Then you have control channel, PDCCH. Then you have data channel, which is PDSCH. So let me stop here. So we can take maybe 5-minute pause, and then we can again start. Or if you have any question, I can take up.
Okay, sir.
Yeah, I have one question.
Yes, please.
Like in 5G numerology, like you had mentioned that like the normal to extended, the cyclic prefix duration, how it is decided, like 1.172 it is extended to 4.16. So is there like any upper limit that has stopped up to 4.16, or like what was the logic in that? Have you observed anything in that?
Okay, let me come to this. Now, why this? First, we need to understand why this cyclic prefix is required. This cyclic prefix is required because we have a one band, like n symbols, that we have divided into smaller subbands. So, for example, you can think like this is the whole bandwidth that we have divided into smaller bands. Now, what happens? This is in the frequency, right? Now, this frequency, the effect on the time duration is that this time duration window has been scaled up. Now you are pumping parallel data of a larger time. Now this forms one packet. But what will happen once there is a similar packet which has been transmitted before and after, a chunk of n symbols. Now there will be some sort of overlap. Now these two, there will be some sort of overlap. Now what we want to avoid that overlap. So what we have done, we have taken some part from here and we have placed it here. Now, how much we should do that? That depends on what is the channel gap between the first channel tap and the last channel tap. Now, the number earlier was 1 microsecond, which has been scaled to 4 microsecond. Now, 4 microsecond, if you translate into the time gap, the distance gap, that will translate somewhere close to 1.2, 1.3 kilometer. We have done 300 meter. 300 meter translates into 1 microsecond. So 4 microsecond will translate somewhere around 1.2 kilometer, right? So that is that is more than enough to support because if the signal is coming, let's say another signal which is coming, let's say of a time gap of 2 kilometers. So definitely larger the gap, the amplitude will also decay very faster. So those signal components will not be does not have enough strength to create some sort of interference. So 1.2, 1.3 kilometer is good number to even sustain for a worst scenario.
Okay.
So that is the
Thank
idea how this number has been come up.
May I ask one question, sir?
Yeah, please.
The delay spread, tau
Yes.
d, we calculated it at 1 microsecond. Yes, sir.
Yes.
It is generally fixed, or it is basically it will change generally. It's based on the
No, it will change. No, it will change. See, yes, it will change. It is not a fixed number. In that example, I have just considered for a calculation purpose that let's say this is that number, but it is not a fixed number. But whenever you design a system, we think from the worst case parameters, right? So that we will be able to handle the worst case delay. So what you can do, you can switch from one numerology to another numerology, normal to extended CP cyclic prefix, if there is a need.
Okay, thank you. In performance metrics table, I have one small doubt. Maybe I am not 100% sure. There is a yesterday's lecture. It is 1 millisecond. Now it is 0.5 millisecond in performance metrics. Can we go to performance metrics slide, sir?
I understand. Okay. So see that number. Many literature that is 1 millisecond, but whatever taken these numbers basically from the IMT 2020, there was a discussion, there is a table, so I have taken these numbers from there. But I have also seen many places where people mention this as a 1 millisecond.
Okay. Yesterday in Ashok Kumar's presentation.
No, that is right. I'm not denying. Many places it is written 1 millisecond. Some places you will find that this is as a 0.5 millisecond. But that is just a targeted number that has been envisioned a long back, what table I'm showing.
Okay.
So once the discussion is started, this was the targeted number we started with as a vision.
Okay, thank you.
Significance research problems presently people can take?
Sorry, can you repeat your question?
Sir, in this part of explanation, any
Right.
significant research problems still people can work on it?
Okay, now what I am doing, I'm just trying to explain what is there, and probably I'm also trying to explain why it is there. Now, research problem is slightly different. Yes, you can take some research problem here also. Like, for example, OFDM is being used. Now, what could be the next modulation technique or another modulation technique that can help you to address these problems? One is OTFS. Probably I have seen one lecture schedule somewhere later in the half. Probably you will learn that at that point of time how OTFS can be used and pose an alternative. NOMA is another candidate which is being considered for, especially for addressing the MMTC use case. So it's not like but what is there now, it has to be like that. Whatever can come, that probably will come into the next release of 5G or maybe in the 6G.
Yes.
So you can take learnings from here, why people have thought something like this, what is there, and then how can we address which has not been addressed here. So in that manner, you can try to pick things and see if you can do carry out some research out of it.
Yes, sir. Because the data is changing day to day, the value of data and transmission of the data is changing day to day.
True, very true. That's very true,
In
and
these
that's why
things,
that's the
the
reason
framework of
research
this thing,
continues.
how we can. Yes, sir.
Yeah, please. You are saying something. Sorry.
No, sir. Within the fixed this framework of this thing, how we can accommodate the data and also accommodate the security of the data. That also maybe thinking, because the presently data is more important.
Yeah, some sort of security part I will be covering. So, so there are different levels of security if you're talking about. So there is a something physical layer security. There are something at a higher layer we also secure the data. So there are enough provisions, but still there is always that is something of the topic. And definitely people are doing different research. You will be able to find something security, physical layer security, higher layer security on 5G, how to achieve those numbers. And they are using different technologies to achieve that.
Thank you, sir.
Yeah, I think we can start now, the second part. So the second part now will be focusing on only on the data part, which is, and that too on downlink data. We call this is referred as physical downlink shared channel. Now, okay, so physical downlink shared channel is used for downlink data transmission, but apart from data, it is also used for something called paging information. So paging information, there are different types of paging. For example, in case of natural calamities, network can pump some information to your mobile device. That is one sort of paging information. Then there are other types of paging information. Similarly, there is something called random access response. So random access response, like I talked about something synchronization. So whenever a UE gets synchronized with the base station, it send a random access, that it send a message to the base station that I also wants to communicate. And then the base station gives a grant to that UE. So that grant also can come over physical downlink shared channel. Then it is also used something called system information. So there is a master information. I talked about MIB. There is something called system information block, that is SIB. So that can also carry over the PDSCH. So we'll be not focusing on these parts. We will be primarily focusing on the data transmission. Now, data transmission is divided into two parts. So this part of the talk, we'll be focusing on the transport channel processing, which basically mainly covers the block number 1 to block number 6. And then there is something called physical channel processing that covers block number 7 to 12. So let me read all these blocks for you. So first block is related with the CRC. I'll be explaining what is CRC, all these things one by one in more detail. There is a LDPC base graph selection. Then there is something called code block segmentation. We are dividing the code block into smaller blocks. Then we perform channel coding, which is again an LDPC encoding here. Then something called rate matching. And then whatever we have done segmentation in third block, we are now again making it a concatenation of all these blocks. Then there is something called scrambling, modulation, layer mapping. Layer mapping is related to your MIMO, like multiple antenna, you are transmitting multi-layer transmission. So it's basically spatial multiplexing. Then antenna port mapping, then mapping it to a virtual resource block, and then virtual resource block to physical resource block. So, and then once you have 12, so basically your resource grid is ready at 12, then we use something called cyclic prefix based OFDM transmission. CPU OFDM based transmission we do after the block number 12. So we'll be starting with the transport channel processing, and the first block here is the CRC attachment. So CRC, so let's say you have what we do, we add a set of L parity bits with the information bits. Now, why we do this? This is to facilitate a block error detection. So there is a block of information. Let's say this block of information of block A number of bits. What we do, we add L number of bits here, and this becomes total A plus L bits. So this is to facilitate the block error detection. Now, a failed CRC decoding. So at the receiver, if there is a failure, you are not able to decode the CRC, then automatically a negative acknowledgement, NAC stands for negative acknowledgement, is triggered, and that initiates the retransmission procedure. So if you have transmit, so this block, we are adding this set of L parity bits to determine once you receive the packet whether you have received it correctly or not. So in case you are not received it correctly, then it will trigger, it will ask the transmitter, or in this case is the base station, to retransmit that entire packet set of bits or that block of bits. So this is called transport block CRC attachment. Now these details are given in 38.212 section 7.2.1. This number is written here. If you are interested, you can read it. So I am explaining the procedure, what is written there in the standard. So it starts with a transport block of size A, which is encoded a block of size B, where B is A plus L. So we take A0, A1, A2, A capital A minus 1. This is your input bit. What we do, we check whether this A, the number of block size, whether it is less than 3824 or not. Now, if this number is, this answer is yes, then we add 16 number of CRC total. So we add 16 parity bits. So L is 16. What we do, we use something called generator polynomial. I will explain how to use this generator polynomial. So there is a sum generator polynomial. We use this to find that 16 bits, and we append those 16 parity bits at the end. Now, if this answer to this question is negative, let's say if the block size is more than 3824 bits, probably 16 bits are not enough. And then we add 24 bit of CRC. So here you can see that the generator polynomial is different now. Now 24-bit CRC is used to add those generator polynomials. Then what we do 24-bit parity. So you can see here there is a bits, and with this A bits we have added 24 parity bits, and this becomes your output. So your output of this block, you have first A bits as it is, remaining L bits are your parity bits. That is the whole idea. Now let us understand through a simple example how this parity bits.
Excuse me, sir.
Yes, please.
Sir, here why the comparison of the block size has been made with 3824?
See, it's a very difficult question to answer, frankly speaking. In the standard, you will find lot of numbers like this. Now, why this is difficult to answer, why this Y part for each and every question? Because for all these things, there is something called study group and working group. So whenever a proposal comes, it goes through study group. There are a lot of company, there are different company and different people from academia, they contribute together. They move it to the working group and they decide these numbers. Now, why exactly they have decided this number is very difficult to answer. But for now, what I can comment, now if you have blocks, smaller block size, probably you don't need too many parity bits. Even 16 bits are enough. But if your block size is greater than a certain limit, probably 16 bits are not enough. You need more number of bits to parity. Now they have used these two sets. Now why not more? Probably if you have too many different combinations, that will unnecessarily complicate the things. Probably that's the reason they might have gone with only two set of numbers.
So
And there are a lot of back calculation also you need to understand, because this is not only CRC, there is a LDPC encoding is happening. So probably LDPC encoding, you know that it can correct the errors. So if there is some error correcting capability. So if it is able to correct the errors, so you might be left with only some number of, probably more number of errors, which is not, let's say in some cases, not being able to correct it by the LDPC encoder. So probably these things can give you some freedom to check whether still there are more errors, or if everything is done. Yeah, please.
Sir, one more doubt I am having. For this A to be defined, or for the condition for A to be defined, whether as like the block code, the data size we are taking as N and D value. In that way, that value of 3824 can be changed out for the research purposes?
Yeah, you can see research purposes, you can change these numbers. There is no harm. Like you can try and see what is the different combination. It gives you like a better, let's say, error protection. Basically, you want to detect the error. So what number gives you a better error detection? You can definitely do that. There's no harm in doing this. But if you're saying
is there
something
any
standard,
standardized method, sir, to get the comparison for this, or any standard value apart from 3824 that has been seen in literature?
see, I can give you some idea. See, if you are really interested to know how the CRC attachment is done, what you go and figure it out, the study groups and working groups related with this 38.212. And 38.212, and all these reports are already being there in document form. So what you can do, you have to download those documents mostly in the Word format. Try to read why these numbers have come up, but it is still possible that you may not able to figure it out, because what happens, different companies suggested some numbers, then there are meetings happens. Those meetings are also very extensive. Sometimes it continues for whole night, whole day, and then they have come up with something. Okay, we will be doing this, or they propose something, and that becomes a part of a standard. So all details you may not be able to find, but definitely you can find why these numbers, or what some insights. But if you want to continue research, probably what you can do, you can see, you already, these things are available on 5G toolbox of MATLAB. You can vary these numbers. You can write your own piece of code, check what is the impact on, let's say you keep everything as it is, LDPC encoder, everything as it is. Select one numerology and change this number and see what is the impact, what is the error detection, which case you are getting the best error performance, and some sort of that. So that can give you some idea. And probably you can come up with new generator polynomial, or maybe you can propose with two conditions, like say 1600, you may have only 8 bits are enough, then probably that will save some amount of bit that you are going to transmit.
Okay, thank you, sir.
Yeah. So now I will explain how this generator polynomial you can use to find the number of parity bits. So this is, I have considered a simple example, because it's difficult to consider 16-bit generator polynomial or 24-bit generator polynomial and do it on a pen and paper. You need computers to calculate for that. Here I have considered a simple message, let's say 11011, and a third degree generator polynomial. So there it was 16 degree or 24 degree. I'm considering here only third degree generator polynomial. So what we will be doing, we'll be doing something, a division operation. So what we are doing, so this represents D3. D square is absent here. You see there is no D2. So the coefficient with D2 is 0, then you have D and you have 1. So this becomes 1 0 1 1. Now this is your actual message 1 1 0 1 1, and then we have added 3 number of additional bits. So the number of parity bits that in this case will be the degree of generator polynomial. So if it is 3, you will be adding 3 parity polynomials. You can see that in the case of previous, it was 16 degree, so that's why there are total 16 parity. It was 24 degree, that's why there are total 24 parity. So we have done the same thing here. Now we are dividing. So if you multiply by 1, it becomes 1 0 1 1. This is simply GF2 operation. That is 1 plus 1 will be 0, 1 plus 0 will be 1, 0 plus 1 will be 1, again 1 plus 1 will be 0. So it becomes 0 1 1 0, and then this we are carrying to the next level. Then this becomes 1 1 0 1. Again we have 1 times of this. This becomes 1 0 1 1. Again 1 1 will be 0. This will become 1 1 0, and now we are picking this 0 here. This is 1 1 0 0. Again by 1 we will have this 0 and 1 1 0. Now this 0 we have carried. Then we have 1 0 1 1. Now this will become 0, and now we are carrying this 0 out here. So this becomes 1 0 1 0. Now if you take this, this becomes 0 0 1. So it means that whatever is the remainder, that will become your parity bits. So or parity bits, or you can say the CRC bits. So this was the message bit. Now this will be translated to this. So your encoded bits after CRC attachment will become 1 1 0 1 1 and 0 0 1. So now instead of transmitting only message bits, now you'll be going to transmit this whole packet. This whole packet will be transmitted to the next block. Is this fine? Let me ask one question. This is not slightly off the topic. We are covering the transmitter part. Can you think what will happen? Yes.
Sir, excuse me, sir.
Yeah, please.
Sir, this is only for error detection alone, right? Not for correction. So
it is only for error detection. Yes.
Okay.
Very true.
Okay.
Error correction will come once we will discuss the LDPC encoding.
Okay, sir.
So basically what we are trying to do here is that we are enabling our data so that we can correct or detect the error. So this is the detection part. Whether there is some error happened after everything we have, is still there is any error left. So my question here is that, let's say you have transmitted everything. How you will be performing CRC decoding at the receiver, because this is the encoding part. How you should do correct, like how you will be able to know whether there is any error happen.
XORing of all those.
So the same code word we have to divide with the same generator polynomial, and we should achieve 0 as a CRC at the receiver.
Right, very true.
If it is 0, it's a no. If it is 0, no error.
No error.
If
No error.
Yes, very true. So what we have to do, this generator polynomial is known at the both the side, user and at the base station. So base station has done encoding. Now UE side, they will also performing similar division operation, but directly whatever message has been received. So if the message has received precisely same, you should get CRC bit as 0 0. The remainder should be all 0. So if it is all 0, it means there is no error. You have received it correctly. If there is any non-zero value, it means there is some error. Then you have to read you will be sending a negative acknowledgement, and there will be a retransmission of the same packet. Okay. So now this is the first module of that entire chain. Now we are moving to the next block, which is LDPC base graph selection. So so let me give you some idea here before we discuss about the graph selection. So this number 1 block was for error detection, right? Now all these blocks from here to here, they are primarily, basically 2, 3, 4, they are primarily for error correction. And block number 2, and that error correction capability will be enabled at block number 4. 2 and 3, basically we are preparing our data so that we can do the LDPC encoding. So in this second block, depending upon the transport block size, and there is something called code rate. Code rate is number of message bits divided by total number of bits. A base graph is selected. Now base graph means LDPC coding has something called block code. It has some block code. This block code is decided based on the base graph. What would be the numbers like in this generator polynomial? What is the yeah. Can you kindly mute Mr. Anushka? Miss Anushka, can you mute yourself? Yeah, so what I'm saying here, that LDPC is a part of something called similar to a block code, where we have generator polynomials, so there is something, a matrix kind of thing, which is having entries of 1s and 0. How that entries will be decided, that is decided based on something called base graph. And in this block, we are just selecting which base graph has to be chosen. So the procedure here is very simple. Again, there are numbers, and it's difficult to find why these numbers have been chosen. Now there is something called if the block size. Now you see this number is A. A is your actual block, not A plus L. If that number is less than or equals to 292, or the code rate means number of message divided by the total number of bits. If that number is less than 0.25, we'll be selecting something called base graph 2. If the answer of this, either of these two are no, then what we'll be doing, we will checking whether A is less than 3824 and the code rate is less than 2 by 3, 0.67. If the answer is yes, then again we will be selecting the base graph 2. If the answer of this, one of these is no, then basically this will be false, and we'll be selecting the base graph 1. So if you translate this to something like a figure, so these are the regions where base graph 1 and 2 is selected. So you can see here, if I divide, this becomes 1, 2. So total there are 6 regions. 1, 2, 3, 4, sorry, total 9 regions. So let me call this 1, 4, 5, 6, and let me call this as 7, 8, and 9. So let's say if you are in the region 1, region 1 means not region 7. So region 7 means you are A is also less than 292 and the code rate is also less than 1 by 4. So obviously you will be selecting the base graph 2, which is blue color. Now region 1, your total code rate is total number of bits is again less than 292. So again base graph 2 will be selected. Region 4, total number of bits is still less than 292. So base graph 2 will be selected. Now if you see region 7, 8, 9, all these regions, so they all have code rate less than 1 by 4. So base graph 2 will be selected. Now if you think about this region number 2, now it is code A is less than 3824 and the code rate is less than 2 by 3. So this region falls under this case. And anything 5, 6, 3, they do not satisfy any of these two. So base graph 1 will be selected. So I'm not explaining what is base graph 1 and 2. We will explain that later. But for now, you understand there are two possible LDPC encoder. One, you can say that encoder 1, another encoder 2. So they are called as a base graph. So base graph 1 and base graph 2. Okay. So now, so this is about the base graph selection. Now there is something called code block segmentation. Now why this block is required, you probably know that this LDPC, which I'm saying, it is something, a generator polynomial, a matrix, generator matrix is being multiplied by some code. So if it is, let's say n comma k matrix, and this is k comma 1, the generator matrix will give you a coded input of n cross 1. So let me call this as something H. This is your message, and this is your coded message. Now this code block segmentation, because it is possible that your A plus L, which is the coded block, like this was your A, and then we have added the CRC, which is L bit. Now this A plus L may not be aligned with your base graph. So what we have to do, we have to break this whole thing into multiple smaller chunks so that we can align with this generator matrix, and this product can happen. So that is the idea here of code block segmentation. Now you can see here we have written to match the code block length as per the selected base graph. The transport block is divided into multiple code blocks, and each code block, a further and additional level of 24-bit CRC is added. So you can think like here, there is a transport block which is having CRC. Now this entire block is divided into multiple number of code blocks, and each code block is again having a 24-bit CRC. Now we'll be discussing how this is being done, the procedure that is mentioned in the standard. That procedure is mentioned something like this. You need to calculate the number of code block. So the first thing is that how many code block will be there. That is the first step. So it's a basically so we have B. We know the what is the B, which is basically A plus L. This is the TB size after CRC attachment. KCB is the maximum code block size. So what can be the maximum code block of one such block? If you have selected base graph 1, this number is 8,448. If it is this could be base graph 2. Okay, so for base graph 1, this number is 8,448. For base graph 2, this number is 3,840. This number can be justified because next number, if you see, this is coming from 3,824 plus 16, 3,840. So if your total bit is less than this number, so obviously you don't need to divide into multiple code blocks. So in that case, you will be not doing any segmentation. Your number of code block will remain 1, and number of bits after the code block will be also the same. So no code block segmentation, no CRC attachment. But in case your B is greater than this size, so what we have to do, we have to divide into multiple code blocks, and so the number of code blocks in that case will be B divided by KCB minus L. Now you can think about, let's say there are 4,000 bits and you are at base graph 2. So what will be 4,000 is a greater number, more than 3,840. So you cannot perform your LDPC coding because LDPC coding has to be aligned with 3,840. So what it does, it just check 4,000 divided by this 3,840 minus L, which is 24, let's say, no, not 24, 16 in this case. Now that number is, now you'll take the floor of this. The floor of this will be 2, right? So total number of code block in this case will become 2, and number of bits after the CRC attachment, it becomes 2 into L, which is 24, and B was 4,000. So because every block you have to add 24-bit CRC. So okay, sorry, this now L is 24 only. This L is 24. So 4,000 plus 224, which is 4048. So total number of bits TB size after transport block CRC and code block CRC will become 4048. And you will be going to divide this whole thing into 2 blocks. So that is the first thing. We calculated how many number of code blocks will be there. It is simple, a division operation. You are just checking whether total number of bits are exceeding this 3840. If it is exceeding, you need multiple number of code blocks. And by what factor it is exceeding, that defines the total number of code blocks. If that number is less than 3840, you basically don't need any code block segmentation and you can directly move to the next block. Now in the second part, once you have already calculated number of code blocks, now you will be calculating how many bits will be there in each code block. Now you have decided there will be 2 code blocks. Now what would be the number of bits in each code block? So that number is K dash divided by B dash by C. For example, in the previous case, we have 4048 is the B dash and C was 2. So it becomes 2024. So this number will become 2024. Now in the third case, you calculate number of bits for matching LDPC base graph size. Now you will find how many bits are required to match the base graph size, because this 2024 may not be matching with the base graph, because this is just you have divided into 2 equal blocks, but this may not be aligned. So you will be finding what is the closest number that is aligned with this K dash. So that number is defined something called 22 ZC for base graph 1 and 10 ZC for base graph 2. This might be becoming slightly more detailed. If you are getting any question, please stop me and ask. So 22 ZC. Now what is this ZC? So there is a table defined in the standard, which I'll be discussing later on. So you can think about this. Let's say this ZC is a number 100. So what you'll be seeing 20. Let's say this, this ZC takes value 10, 20, 30, 40, and 100, 110, something like number in an interval of 10, 20, 30, 40 goes up to like that. So what would be the closest number? The closest number in that case will be, if you take 20, 22 times 100, this will become 2200. Probably that will be the closest number of this. So we have to add some filler bits. So whatever remaining number, we have to add some filler bits. Basically, we will be adding some zeros to make it 22. So now finally, this is the last step. So what we are doing, so we know what is the number of code blocks. We know what is the number of K, like number of bits in each code block and K. So we start with, let me complete this whole thing. Okay, now let me explain. So what we are doing, we have a bigger code block. We have to divide this into, let's say, 2 code blocks. Let's say the C is 2. Now some bits will go here. Some bits will go in this code block. And then each code block, you are going to add some 24-bit CRC. That procedure is explained here. Now, how this is happening? You'll be starting with something, setting I and K both as 0. Now CRK. Now K is 0. R is also set to 0. So this becomes C00. So this is your first code block. You'll be assigning first bit BI here. Then you'll assign B2, B1 here, B2 here, something like this sequentially. And you are going and you will check whether C is 1 or not. So in this case, we have to divide into 2. So this answer will be negative. We will be directly moving to this part. We will keep on doing this whole thing until we reach at the last K dash minus L minus 1 symbol. And once we reach that, what we will be doing will be stop taking symbols from here. And then we will add 24-bit CRC and add those CRC here. And then next bit will go into the next code block. And this is the way this whole thing is designed. This whole procedure is designed. So now till this stage, what we understood is that you have a transport block. There is already some base graph we have selected, which has some dimension. Now, based on that dimension, we are dividing this into multiple code blocks. Once it is done, then we perform the LDPC channel coding. Now, this is the part which enables your entire data so that a receiver end, you can correct the error. So it enables error correction capability. So far CRC, they are just facilitating you error detection. Now this enables you to correct the errors. If there is any question, we can take. Okay, so so let's move to the LDPC channel coding part. So channel coding, we know that LDPC stands for low density parity check code, and it is an extension of linear block codes where k bits in a code block are encoded to n bits, and it is used for error correction at the user side. So you can see here, if you pay attention to this diagram, now it is showing there are multiple layers. Now each code block has to be encoded parallelly. So now you have divided a bigger code block into a smaller code block, segmented it. Now each segment of the code block has to perform an LDPC encoding, and that will give you some n bit of information. So you can see here also we have n bit of information, k bit of information is input, output you are getting n bit at each layer, at each segment of this code block. So before we move, let me give you some review of linear block code, how it works. So I have considered a 7,4 Hamming code, and which has the following, this parity check matrix, this H. So this is not a generator matrix, but a parity check matrix. So parity check matrix, and that is also a systematic parity Hamming code. So you can see here for any valid code word, this should satisfy H times the C transpose, where C is your code word, where first few bits are your message bits and remaining are your parity bits. So H times C transpose should be 0. M message bits, P parity bits, C is the coded bits. So how can you use this H to find what should be the parity bit? So how we can do that? You can write this into form of two matrices. So what we are calling this first part as H1, the second part, which is an identity matrix, I'm calling this as an H2. H1, H2, this transpose is not required. M, P transpose, this must be 0. Now if you multiply this, this will become H1 M transpose plus H2 P transpose as 0. Now, if you simplify, this will become P2 P transpose as H2 inverse H1 M transpose. Now, but H2 is an identity matrix. So identity matrix inverse is an identity. So if you take simply H1 and M transpose, you will get the parity matrix. So in this part, we will try to understand how this parity bits can be calculated using the parity check matrix, which is defined in the standard. That depends on the two base graph we are talking about and how that works. So LDPC code also retain the same structure which we have seen in the case of Hamming code, but there is a two difference. The size of this is very, very big. Like the previous case, it was 7,4. So it has how many rows and columns? 3 rows and 7 columns. So here you will see it's a very big parity check matrix. And in this very big matrix, there will be very few ones, and most of the places it is 0. So that's the called the low density parity check matrix. So this is the idea. You have two base graph. The number of bits in a base graph will be 22 ZC and 10 ZC. I have not yet defined what is ZC. For now, you can think like ZC is a number which is coming from the higher layer or the top layer. Now this K bit of information will be translated into N bit of information. Now N is again also defined. This will be 66 ZC or 50 ZC. So if you are selecting base graph 1, your code rate is fixed to 22 ZC divided by 66 ZC. That is code rate, right? K by N, which is 1 by 3. Now, if you are choosing base graph 2, the code rate is 10 ZC divided by 50 ZC, which is 1 by 5. Now, this ZC here represents an expansion factor, which I will explain. So now there is a table in the standard that defines different possible ZC values. So there is something called ILS index. Now this index is coming from the higher layer, this index. So let's say the higher layer communicates the value ILS as 1. So the choices of ZC is restricted to these many. So 3, 6, 12, 24, 48, 96, 192, 384. So whenever you are finding K, so this KB times ZC should marginally exceed K dash. Now K dash was the number of bits in each code block, segmented code block. In each segment of code block, the K dash was the number of bits. And K, which is we have written as 22 ZC or whatever, 10 ZC or 22 ZC. Now this should marginally exceed. So if that number, like earlier we have number 2024. Now if you see that 2024 number, what should be the ZC here? Can someone think and answer? So let's say we are having base graph 2. So base graph 2 means 10 ZC. So what we want, 10 ZC should be greater than 2024. What value of which ZC we should pick? Let's see if you are picking 12. So it will become 1200, which is less than 2024. If you pick 24, it will become 24 into 10, 240, which is still less than. Let's say you pick let's say pick you 96. So it will become 960. If you pick 192, it will become 1920. So you have to pick 384. Then only 384 into 10 will become greater than 2024. So in that case, you have to choose ZC as 384. So it depends on which configuration we are playing with. So we have to choose ZC accordingly. Now, this is just a relation. If you do not want to remember how this set is defined, so this is something defined like A into 2 raised to the power L, where L varies from 0 to j minus 1. For example, in this case, A is 3. So the first number is 3. Second number is 3 into 2. Third number is 3 into 4. Fourth number is 3 into 8. Then 3 into 16, 3 into 32, 3 into 64, 3 into 128. And it goes up to 2 raised to the power 7, which is 128. So this is how this table has been designed. So this is the first step where you find the appropriate ZC. Now, this KB, which we are discussing, now this value 10, 22 ZC, 10 ZC, this value can also vary depending upon the B size. So far, I have not explained like this. This is the first time I'm explaining. Like earlier, I have just mentioning 10 ZC, but this value of KB can be 9, 8, or 6, depending upon the total number of A plus bits after CRC attachment, that is A plus N. So this is the first procedure. The second step, what we do, we assign the message bits. So we have C0 to CK minus 1. This is my segmented code bits. What we do, we assign these bits to the encoded bit stream. So you have this coded, let's say this is the one segment. Now this is your D. So this is overall length is K. This will become N bit. So this will be assigned somewhere here. Now you see, pay attention. This assignment starts from 2 ZC. So CK. So if CK is not a null, in this case, we will be assigning something like this. So this CK will be assigned to D0 of this will be C. So we are not assigning this part. We are assigning this part here. So your D0 is D2ZC. Sorry, D0 is C2ZC, something like this. So this way, this assignment. So this is something a shifted window. So all the bits here will go somewhere here. And this is the way we repeat this whole procedure, and all the bits are mapped. Then what we do, we try to find the parity bits. So we have this whole packet. We have map 2ZC, sorry, K minus 2ZC bits. Now we will be filling the parity bits, N plus 2ZC minus K. So total length is N. So this bits is N plus 2ZC minus K. So this sum will be N only. So these are my all parity bits. So this is my coded bits, and this becomes your parity bits. So C and P. So now there are two base graph here. One having a dimension of 46 × 68, another having dimension of 42 × 52. So, okay, before we move, let me explain. So this H, now how this has been designed in the literature, like the standard, like this is not, so this is a base graph, which means that it has 46 rows and 68 columns. So if you're talking about this, this becomes 46 rows and 68 columns. The interesting part here is that this each element of this is not a scalar quantity. This itself is a matrix. And that matrix is of dimension ZC × ZC. So you can think of, if you remember the ZC table, you can see here what is the biggest number. I think biggest number is 384 in this entire table, and in smallest number is 2. So if you're having 384, this matrix which I'm referring now, what would be the dimension? This will become 46 into 384. So the total rows will become 46 into 384. This many rows. And the columns will be, how many columns? 68 into 384 columns. So you can think of the size of this parity check matrix. It's a huge matrix. It can be a huge matrix depending upon the value of ZC. So minimum 46 into 2, which is 92 times. So minimum value is 2. So it will become 92, 46 into 2 times 68 into 2, which is 136. And the maximum dimension will be this, which is somewhere 18,000 times 24,000 or 23,000, something like that. So it's a very big matrix. Now, what are the entries of this whole matrix? That is defined through this procedure. So this I have taken from the standard as it is. But before we move, let me try to explain what is happening here. So the element of edge with row and column indices that is defined are of value 1, and all other elements are of value 0. So there is a table, something like this, which is defined. So what you can see here, row index 0 and row index 0. It is defined. So let's say this ILS, which is the higher layer, it is set to, let's say, value 2. I'm just assuming that this value is set to 2. So what you will be checking, 0, 0, it has some value, right? 73. So you will go and you will create a 46 cross 68 matrix first. And what you will do, you will make this entry 1. For example, you see 0 and 4. 4 is not there, right? It's 3 is there, 5 is there, but 4 is not there. It means 0, 1, 2, 3, they will be all 1, 1, 1, and then 4 is absent, so you will make it 0. Something like this, you will be creating that table. So once you create this 1, 0 table, that is the first step. What we'll be doing, now you will replace all these 1s and 0 by a ZC, ZC matrix. So wherever is 0 is there, you will make that 0 as a 0, all 0 matrix of dimension ZC, ZC. And wherever 1 is there, you will be again go back to this table and check what is the number written here. Okay, this number is 73. So what you will be doing, you will go back and you will be doing some operation like this. We will do a modulus operation. So 73, let's say this ZC is 22. I'm just assuming. You will take this modulus. Now this modulus will give you what is the value? It will be 66, 7, right? It will give 7. So you will be creating an identity matrix of dimension ZC, ZC, and then you will be circularly rotate that matrix by 7 columns. So your seventh last column will become the first column. The last 6th column will become your first column. So something like this you'll be doing in the circular rotation. So that is the whole procedure. You get that big 1, 0 matrix. Let me explain this through one very simple example. What I have done, I have taken a very simple case where only ZC is 5, and this is the number written here. So what you can see here, I intentionally placed all the numbers. So you can see here 0, 0, this number is 1, 0, 1, this number is missing. So that implies that this number is 0. So missing numbers are 0 here. So what we do, we create a total 4 rows, 8 columns. So it becomes a 4 cross 8 matrix. Now, wherever the number was absent, that is simply written as 0. It's like 0, 1, is 0. 0,6 is 0. 0,7 is 0. Now other elements are I of 1, I of 3, I of 1. So basically it's an identity matrix. 1 means you will be going to circularly shift those elements by 1 column. Similarly, I of 3, you are going to circularly rotate by 3 columns. That's it. So this way we create the H matrix. Now all these I and 0 are not, they itself as a matrix of dimension 5 cross 5. So something like this. Your I is simply identity matrix. 0 is all 0 matrix of 5 cross 5. I of 1, you can see here, first 0th column becomes first column becomes second column, and the last column of this identity matrix will become your first column. So it's basically rotating the columns of identity matrix in this manner. Similarly, I2 means you are rotating by 2 columns. I3 you are rotating by 3 columns. I4 you are rotating by 4 columns. So this is the whole idea, and this gives you this matrix. So this is the way you can create the big matrix. There is a one interesting part here is that there is something called, if you see this part, these are II matrices in 2 diagonals, and this structure we call as a double diagonal structure. And this is adopted in 5G. Although I have taken a small example, but I try to explain what is this double diagonal structure. There is an advantage of this double diagonal structure, but if you see the bigger matrix, this looks something like this. So wherever you see the green dots, they basically represent 1. Wherever there is a empty space, they basically corresponds to 0. So it is, you can see like 52 cross. So this is your 68. And what was the base graph 1 dimension? If you see, go back, this is 46 cross 68. So there are 46 rows. So this dimension is 46 and this is 68. Now this particular part I was talking as double diagonal structure. You can see there are 2 parallel dots in both. So this has the double diagonal structure. Now this is about base graph 1. Similarly, base graph 2 also has a similar structure. Now, so what I'm calling this, I'm calling at this part of the matrix as A, B, T, C, D, E, something like this. So this part of the matrix is A, B, C, D, this part as T and this part as E. So basically I'm writing this whole block into 6 sub-block matrices, A, B, C, D, T, and E. So if you write something like this, and you write this as H, M, P1, P2 transpose. P1 is again a set of parity bits related to the double diagonal structure, and P2 is the set of parity bits related to the single diagonal structure. Because if you see this part is single diagonal. This part, the above part is only double diagonal. So it is something like this. So if you apply some simplification, you will get something of this nature. So your parity bit 1 and 2 can be written like this, P1 and P2. So I'm not explaining how you can derive this. If you're interested, you can easily find out. These are all available. There's a book by Christopher Cox. If you are interested, you can read that book. The derivation is given in that. Then there is the encoding procedure. So now we got the parity bit. So what we do, remaining bits will be filling with the all k to n plus z2 zc minus 1. So initially few bits are your coded bits, The remaining bits are your parity bits that we are filling one by one. So this is the way we do this LDPC encoding. So LDPC encoding, now we have coded and parity bits all together. And this you need to first generate that channel matrix, and that requires that bigger table, those values, picking up those values, creating a channel matrix. Sorry, parity check matrix. Any queries so far in this LDPC encoding part? I can understand this might be slightly more mechanical, but I hope you get the gist what is happening inside the downlink data processing.
Sir, can you tell the significance of that double diagonal and single diagonal matrices? What actually they are representing?
Okay, I will give you some idea because that will take a lot of time to explain what, but I will give you some simple idea. Let's consider this matrix, this one. Now, if you try to simplify, let's say you want to find the parity bits. So how many, there is a message bit. So this particular part, sorry, 1, 2, 3. Yeah, this particular part corresponds to your message. These up to this, and the remaining part corresponds to your parity. Right. So how many message bits are there? Let's say 4 message bits, 4 parity bits. M0, set of bits, M0, M1, M2, M3. Then let's say this is P0, P1, P2, P3. Now, if you multiply all these, you will get 4 equations. Now, if you sum those 4 equations, what will happen? Because there is a I plus I, they are aligned. So you can, that will become 0. So if you add all 4, what will happen? This will become 0. This will become 0. And this 2 will get added and become 0. So, and this I2 will be again 0. So you can easily find some parity bits just by a very simple operation of addition. And then you can start doing backward substitution. Like you find this one, you plug it into the one equation, and you can use the backward substitution, and you can easily find P0, P1, P2, P3. So that is the idea. It makes your entire thing very simple. You don't need any matrix inversion. Simple by addition and backward substitution, you can find all the parity bits. So that is the idea. It has been retained in, like it has been taken in the standard, so that it makes the processing simple. Is it clear?
Somewhat clear, sir. So that in simple, we can say redundant data removal we are going to do with this.
So what we are trying to do here? First, we need to understand. We have message bits. We want to find our parity bits. Now, to find the parity bits, if your structure requires more complex operation, it will become too burden on the system, right? So they want a simple operation. Now, because of this double diagonal structure, you can find you can simply create multiple equations. You sum 2 equations, one will be added to 0, and you can find the parity bits related with another equation. And then you start doing backward substitution. So that is the idea. So what you do, you can create 4 equations right here. If you multiply, you will get 4 equations. You sum 1, 2, 3, 4 all together. Once you sum, you will get some message bit here, summation of message bits. You will get some summation of this parity bits. Because of the identity, then once they will be sum, they will become 0. This identity will get sum and will become 0. They are not perfectly aligned because of the matrix, the way I have written. But you can understand this is the last element, right? These two corresponds to the last 2 element of that second and third row. This I is the third last element in the first equation, and this I is the third last element in the second equation. So once you sum, I plus I will become 0. So you don't need to do any calculation. It will be simple. You will be left with only one parity bit that is related with the P0, and you can easily find the P0, and then you can subsequently find P1, P2, P3. So that is the way.
Okay, sir. Thank you, sir.
Okay. Okay. So I think this is the LDPC encoding. Now, what we are trying to do, rate matching. Rate matching, it is something we have know that 22 JETC bits are mapped to something called 66 JETC, right? If you have chosen base graph 1, which is code rate 1/3. Now 10 JETC, if you are base graph 2, it becomes 50 JETC, which is code rate mean 1/5. But in a system, you don't need a very specific code rate 1/3 and 1/5. You may have different, you need to support different code rates. So it is rate matching is used to match with a predefined code rate. So as a system, you want to transmit, let's say 1/2 code rate, and you are at, let's say, base graph 1, which has given redundancy of like every 1 bit, there are 2 redundant bits. But you only want to transmit, achieve a code rate 1/2. So what you have to do, you have to discard few of the parity bits, and so that it becomes 1/4. Oh, sorry, 1/2. So this out of this, let's say this 66 JETC, if you drop last 22 JETC parity bits, so what will happen? It will become 44 JETC, your output, and your code rate will become 1/2. So the rate matching is an operation through which we discard few of the parity bits to match the desired code rate. That is the idea of the rate matching. Now, and it also do another operation, something called bit interleaving. This we will be discussing later on. First, let's understand how this like dropping is done. So dropping is done something called bit selection procedure. You select few of the bits and like how many number of bits you want to keep and how many bits you want to drop. So there is a formula here. Okay. This formula is used to find the number of bits that you want to keep. So you have n bit of message, but you want to keep something e number of total number of bits. Here you can see there are different parameters, NL, QM, G, what they are. So G is the total number of bits available for transmission. NL is the number of transmission layer. So how many parallel stream of data that you want to transmit. This will come once we'll discuss the physical layer part. QM is the modulation order. So if it is a QPSK, this value will be 2. If it is 16 QAM, this value will be 4. And likewise, C dash is the number of total scheduled code blocks, and J is a running index. So this E will give you basically what you are doing. There is a formula. We are using that formula to find the number of bits that we are going to transmit. And that depends on how many number of layers, what is the modulation order, and how many code blocks that we are going to transmit. And now, once you know that value E, probably you have to do some sort of puncturing and shortening operation. So shortening operation, like for now, I can say that what we are doing, basically, we are discarding few bits from here. So that we call as a puncturing. Sometimes, so whenever you are disturbing the parity bits or removing some parity bits, that becomes a part of puncturing. That sometimes we drop some bits from here, that becomes a part of shortening. And this region represents your message bits. So sometimes we do removal of message bits also, with a belief that whatever we are dropping, they can be recovered through the parity bits, using the parity bits. But mostly puncturing operation is performed. which is basically dropping some of the bits from the end. So this is a puncturing and shortening operation. Now there is another operation is done, something called interleaving within the rate matching block itself. Although this is not related with the rate matching, but in the standard, they kept it as a part of rate matching block itself. So basically you have now total E number of bits. There is a relation given in the standard. I will not go to the relation, rather I will try to explain what is happening through a pictorial diagram. You can see here, these are your different code blocks. So this is first code block, which having E messages. Then there is a second code block, which is again having E messages and something like this. So, okay, sorry, my mistake. So they are not code blocks. They are the same code block, but these are the, let's say you are using 16 QAM. So these are the first 4 bits. These are the next 4 bits. And these are the next 4 bits. What we do, so basically we are clubbing them in this pattern of 4 bits, depending upon the QM. And then we arrange them in this order. So E0 to E1, first we arrange like this, then this, and then this, and then we read like this. So what will happen? This color bit will go here. This color will come here. This color will come here, something like this. And then this E1 will go here like this. So it's basically jumbled up procedure. And this jumbling up is happening based on the QM, which is the modulation order. That is the idea. So what we do, we arrange them in a matrix, all the bits. So first we are arranging in row wise, and then we are reading in column wise. So some jumbling, and this will have total number of bits in each column will be QM. So this is the whole procedure. So this will have basically QM. So this matrix is QM times some number of bits, E by Q1. So that total number of bits are E. So let me summarize this part. So we have understood that there is a bit selection procedure happening, which using this N bit, we are finding only E bit of a stream. So N becomes E, where E is less than or equals to N. Then there is an interleaving. And after interleaving, we are getting, so these bits are jumbled up here. And once we have done this, now what we do, we have so many different segments. So this is, let's say, one code block, one segment. This is another segment. What we do, we stack them all together in a series fashion. So this becomes your first, then this becomes your second, and likewise. So you can see here till this point, there are multiple layers. Now after this, it becomes a single stream of bits. So this completes the discussion of the physical, transport channel processing in this. So, and after this, your physical channel processing, which is start number 7 to 12. So let me recap here. So we understood the detailed procedure for transport channel processing during the 5G downlink data transmission, which includes these operations, CRC attachment. So you have A bits, it becomes A plus L. Then we have base graph selection, where you have selected whether you have to use base graph 1 or 2. Both has different parity check matrices. Then we have divided this bigger A plus L into smaller multiple segments. Each segment will go through a LDPC encoder. Then we have matched the rate of this encoded output, perform an interleaving, and then we have combined all these code blocks and make a bigger bit of strings. So that is all about here. And these procedures enables the error detection and correction capabilities in your information. So any question, we can take it now.
Can I ask one question?
Yeah, please.
The puncturing like we generally do, then how the puncturing is different from rate matching? Is it the same or like it is different? Puncturing of the bits and the rate matching.
No, rate matching, we wanted to achieve. Puncturing is the method through which we are achieving it. So rate matching is that you want to discard few of the bits, but which bits you will be discarding. So that comes from the puncturing operation. So puncturing operation gives you I have not explained that part in much detail. Standard specify which bits has to be punctured. So usually the puncturing happens from the end. Like you have a parity bit, so you try to discard the last few parity bits so that you can achieve the desired code rate.
Correct.
So if you want, we can take a small break here and then again continue for the last part.
So if you one more question, like if you compare this LDPC with turbo code in 5G. So because in the 4G, like it was the one of the important component. So how this turbo code is not suitable for 5G or like where it starts?
Okay. So if you see 4G and 5G, if you compare, exactly turbo has been replaced by LDPC.
Correct.
Now, why it has been replaced? Because LDPC has been proven that it can give you better capacity gains. It has better error correction capabilities. So that is the only reason turbo has been replaced with the LDPC in 5G.
So only the performance parameter, the error correction capability.
Yes,
but in terms of computational complexity, both are they same?
No. Obviously, this is easier to in terms of that you are talking about the receiver complexity and the parity check bit matrices. So it is easier to compute here. So if you think about turbo, that is something called BCGR algorithm is used, which is an iterative algorithm and requires a lot of computational resources. LDPC decoding can be through which a belief propagation algorithm, Tanner graph methods are there, which can be used to detect the error. So this is slightly low complex, like the complexity is the lower side. That is also one reason. But the primary reason is that it has a better, it has been proven that it can achieve the very close to the Shannon bound. And that is the reason LDPC and polar code, these two have been introduced in 5G and replacing the turbo which is used in the 4G communication.
So where is the challenge? Like if someone is taking the problem in this area, like so where still like we are facing the challenge? Where is the scope we can continue further?
Okay, see the scope here is that you can design better algorithms, which is a low complex algorithm. So that will, because see there are two parts. One is standard, one is your
non-standard.
The receiver part, which is non-standard. Standard basically defines the operation at the transmitter. So either you use the standard and try to improve the algorithm part of the receiver. So that could be one research problem. If you want to contribute into the standard, so then you need to figure it out, the challenges or the current limitation of the standard. And then there is a lot of procedure, like you have to first participate through some standard body. Like for example, we have TSDSI in India. You have to participate your contribution through that, and it will go through multiple rounds of discussion. Probably if it got accepted, it will become a part of the standard, and that will take. And once it is part of the standard, that's where you can contribute in terms of standard contribution. So either you assume that the standard is freeze, work on the receiver part, or if you want to contribute anything towards transmissions, then probably you have to keep update yourself with the current release. What are the things they are going on discussion? There are a lot of study items. You go to the 3GPP website, check what are the study items are ongoing, try to read them, get your updated, that is basically a literature survey kind of thing. Then try to contribute something and then push it through any of the standard body.
Correct. So which one is more popular, like irregular or regular one in the 5G? Like LDPC LDPC also are two types, right? So that regular LDPC codes, irregular LDPC codes. So which one is more like popular in that case?
No, whatever we are discussing, they are regular LDPC codes only.
Regular LDPC codes, okay.
Yeah, whatever we are discussing, they have definite block size, definite all the arrangements. They are all regular LDPC codes, same. But there are different permutation combinations are allowed, so that you can have different, depending upon the need, you can tune to different combinations. If the channel is worse, probably you need more protection, better error correction capability. You can go with the, let's say, base graph 2. If you have good channel condition, probably you can go with the base graph 1. So that way you can switch between different.
Thank you.
Sir, I have a question.
Yeah, please.
Yeah. How important is rate matching, and can it be skipped as in the process of error detection and correction?
No, it cannot be skipped. The reason I'm explaining, there is let's say you have a transmitter having 2 antennas, and you are using QPSK modulation. How many symbols you can transmit? Let's say there is one subcarrier. A very basic question. Consider one subcarrier, 2 antenna, and you are using QPSK. How many bits you can transmit at each symbol? 2 into 2, 4 bits, right?
Yeah. Yes.
Not more than that. Now, let's say if I have more number of bits, let's say what you have in that packet, let's say you have a transport block, which is, let's say, 102 bits. So what you will be doing, maybe you will transmit 25 symbols of 4 bits. Once you reach at the end, you have now left with only 2 bits. So you have to somehow either make this 2 to 4, or you have to make this 2 to 0. Discard those 2 bits, or you append to 0. So in that sense, that rate matching also does this job also. Apart from matching the code rate.
Okay.
So you cannot completely ignore it. It has to be there.
Okay, sir. Okay. Thank you, sir.
Yeah. Okay, now let me move to the next or the last part of this. So it's 12:30. So I will be skipping few parts here so that we can focus on the important things. So the first module on the physical channel processing is the scrambling operation. Now, scrambling, there are various purpose scrambling is done. So scrambling is an operation where what we do, you have a bit stream. You XOR this bit stream with another bit. So it gives you some sort of protection from any unauthorized access. So what I mean to say that you have a bit stream, let's say 1 0 0 0 0 1 1 0 0 1 and 0, something like this. And then you have maybe another bit stream 1 1 0 1 1 0 0 0 0 1 1, something like this. Now this is your actual bit stream coming after that block number 6. And this is your additional bit stream, a scrambled bit stream. So now this, you will do the XOR and you get something, let's say 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, something like this. So now anyone, if it decodes, it will able to decode this, not this. So that will give you some sort of protection from any unauthorized access. So that is one reason that this is used. Second, it is possible that your this bit stream is not properly randomized. Now, what is the randomization means? Usually we assume whatever analysis we do, we make an assumption that like if you have done any information theory course, you might have remembered entropy. Entropy gets maximized if the bits are equally likely. So this scrambling some sort of gives us a freedom. If there are long sequence of ones and zero, by doing this scrambling operation, probably you'll be able to reduce the bits and improve the like make the zeros and ones more equally likely. It will also help us to reduce the interference. Maintaining the synchronization. Synchronization, now you think about, again, there is a long sequence of one. What will happen? You will have this kind of a pulse. So if because of this scrambling, you will have very like something like this. So this, because of the long sequence, sometimes the receiver gets desynchronized because the clock, it is moving for a long time. Because of this scrambling, now there is a lot, too many toggles will happen very often. So that will help to maintain the synchronization. And also it helps to support multiple transport blocks. So in 5G, whatever we have understood in the transport channel processing, 2 transport blocks can be sent parallel by one device. So that also, because now both these will have different scramble. So this sequence will be different. So you can support 2 different parallel transmissions. So that is one idea of the scrambling. Now, what is the procedure? So there is something called, we have a bit stream this, and there is a scrambling sequence CQI. You add them and do a modulus 2 operation. So basically XOR operation we are doing between these 2 streams. Now, how to generate this CQI? Now this CQI is generated by taking an XOR of 2 M31 gold sequences, which is X1 n plus 1600. So X1 is one sequence, X2 is another sequence. And we are taking the modulus of this. This would be I, not n. So C of I is X of I plus 1600. So whatever sequence we are generating, we are taking an offset by 1600 place of both the sequence, and then we are taking the XOR, that becomes our C of 0. So C of 0 will be X1 1600 plus X2 1600, where X1 can be found through this recursive relation and X2 can also be found through this recursive relation. So these relations are given, well defined in the standard. Now, if you have to use any recursive relation, you need some bits, some initialization of few bits. For example, we are starting from n plus 31. So if you put n0, so you will be getting x1 31. So first 31, 0 to 30, those bits has to be initialized. Similarly, in x2 n plus 31, first 31 bits has to be initialized. So that initialization procedure is something like this. So in the case of x1, it is fixed that first x1 0 is 1, remaining 30 bits are 0. So it becomes basically 1 and followed by 30 zeros. So this is the initialization of x1. The initialization of x21, it depends on something called C-init value. Now this value is a unique value, and what we do, this is a 31-bit number. What we do, we convert this to a 31-bit binary form. Whatever is the number, LSB of this will become x20, MSB of this number, 31-bit equivalent number, will become x231. Now here you see there are a lot of parameters. Eta ID is the cell identity through which you are attached, or it can be a number if higher layer is configuring. So a random number which is higher layer is configuring, or otherwise a physical layer cell identity is used. Now Q is represents the code word index. It can be 0 or 1. Eta RNTI is again configured from something called radio network temporary identifier. So now because of this recursive relation and this C-init value, it is, unless these two are known, you cannot find what is the actual sequence. And that gives us a protection from any unauthorized access. So this is one part that is done in the physical layer processing. So now you have another bit stream, which is the scrambled bit stream. Once we get that, what we do, we perform the modulation operation. So modulation operation, now basically what you do, you pair few bits, let's say 0, 0, that will be mapped to, if it is a QPSK, it will be mapped to 1 plus j. If it is 0, 1, will be mapped to, let's say 1 minus j, something like this. Or if it is 16 QAM, the mapping will be of 4 bits. If it is 64 QAM, the mapping will be of 6 bits. And if it is 256 QAM, the mapping will be 8 bits. So what we do from the bit stream, we are picking pairs of bits and we are mapping it to one complex number. So QPSK, basically this is the relation is given, and this leads to these 4 possibilities. So if it is 0, 0, it will be mapped to 1 plus j. 0, 1 will be mapped to 1 minus j. 1, 0 will be mapped to minus 1 plus j. 1, 1 will be mapped to minus 1 plus j. So if you draw a constellation, so something like this 0, 0, this will be 0, 1, sorry, 1 minus j. This will become your 1, 1, and this will be your 1, 0. Minus 1 plus j. So this is the way this mapping is done for QPSK. Similarly, if you read the standard, all 16, 64, 256, this has been defined. Okay, so this is about the modulation. Now, if I move to the layer mapping, so layer mapping is now you have a complex symbol. Now this complex symbol has to be transmitted from multiple layers. So you are creating a bit of a stream. So let's say these values are complex number, let's say x1, x2, x3, x4. So what will happen? Few information, let's say x1 will go from this layer, x2 will go to this layer, x3 will go to this layer, x4 will go to this layer. So all odd number index are going here, all even numbers are going here. So this is something a layer mapping. Now, so this is equivalent to spatial multiplexing. You might have heard of this if you have read MIMO. In a multiple antenna system, it is used for transmitting parallel streams of data. Maximum 8 parallel streams are supported in 5G standard. And this is a table where you can see here how this is being mapped. So if it is, you can see here number of layers, number of code words. So if it is 2 layer and 1 code word, if you see this, what is happening? All even numbers are going here, all odd numbers are going here. So all even 2i, 2i plus 2, 2i plus 4, they will go here. 2i plus 1, 2i plus 3, they will go into this layer. Similarly, if you think about 4-layer transmission, so you can see that this information is going to the first layer, then next information is going here, third information is going to the third layer, fourth is going here. Again, this one will go to the first, then next one will go to the second, then this will go to the third, and then again this will go to the fourth. So something like this. So this corresponds to this particular case, 4 layer and 1 code word. So, so if you talk about all these things, there is something called an interesting concept called antenna port mapping. Now, if you remember, if you go back to the initial slide, I was talking about there is a resource grid, and this resource grid may carry different sort of information. Now, what we do in antenna port mapping, we give those data a different number. So, for example, if it is a PDSCH data, we are giving us something called port ID 1000 to 1011. So 1000 to 1011, it is to support 8 layer. So 1000 may be layer 1 data, 1001 may be layer 2 data. So we are creating parallel grids. It's not single grid, parallel grids, and we are assigning them a unique number. That is the idea of port mapping. And then once it is assigned, we map all those data to a virtual grid. So this virtual resource block, so it's a virtual resource block. Why we are calling? Because every channel will create, like every port ID, there will be one virtual resource block. Now, but while transmitting physically, different sort of information has to be summed together, and it has to be transmitted on the physical resource block. So that part, what we do in the next, what we do, we assign this virtual resource block to physical resource blocks. So different sort of information, they will come and multiplex together, and there is a possibility of further interleaving. So there is a direct mapping. So VRB, whatever is there, directly going to the PRB, or then you can also interleave the data. Means the data at this location may go somewhere here of the physical resource block. Data at this location may go somewhere here to the resource block. So that is two types of mapping are performed. So this is when there is a no change, whatever is here, that is directly going here to the physical resource block. And here you can see that this chunk of data is being mapped somewhere here. This chunk of data is being mapped somewhere here. So all those sort of interleaving are also allowed. So once we have this resource block ready, what we do, we map this information to the physical resource block, and that becomes, and then we use the cyclic prefix based OFDM to transmit the data at this location, which involves the operation of IFFT, parallel to serial conversion, and your addition of the cyclic prefix. So we have covered scrambling, modulation, and layer mapping, and we briefly covered this 10, 11, and 12. So let me summarize this part. So in this part, we understood the detailed procedure for physical channel processing during 5G downlink data transmission, which involves scrambling, modulation, and layer mapping. These are the three key part of the physical channel processing. And then we have antenna port mapping, basically assigning a unique number to different layers of information, then mapping it to a virtual resource block that can directly map to either physical resource block directly or in an interleave form. And these procedures prepare the signal for MIMO OFDM based transmission, or you can say massive MIMO OFDM based transmission. So if you have any query or question, we can take this now, at least in this part.
That layer concept not clear, sir. We are unable to really what that real layer concept we are not received properly. The concept of layer.
Okay, I will go back and try to explain once.
Simple example, if possible, some simple.
Yeah, I will. So okay, So what is layer? If you think about MIMO, so MIMO usually has multiple antenna. That implies that MIMO has multiple antenna. Let's say you have 2 antenna. Now it's up to you how you want to use this antenna. So this antenna can be used either you can transmit 2 different symbols. Let's say you are transmitting X1 here, X2 here. This we call spatial multiplexing. That gives you an spatial multiplexing gain because at the same time now you can transmit 2 streams of data. Or what you can do is let's say you don't want to do this, you can transmit same information from both the antenna. That is also possible. So either you can transmit 2 different streams or you transmit the same stream. If you are transmitting same stream, you will get diversity gain. You are not getting any spatial multiplexing gain, but you are getting diversity gain. Now in 5G, they have created this layer mapping to get advantage of spatial multiplexing gain. So, but there could be various ways people can do this spatial multiplexing, right? Someone can do, they can transmit X1, X2, X3, let's say from first antenna, then X4, X5, X6 from the second antenna, and then maybe X7, X8 from first antenna, X9, and X10, 11, and 12 from second antenna, right? This can also be possible. But if you do that way, this becomes non-standard way of doing it. Because if there is a reason why this layer mapping has to be standardized. People should not able to do in various possible permutation combination. Now they have fixed this permutation combination. What they said, like if you are having 2 parallel stream, so you transmit X1 from here, X2 from here, then X3 from here, X4 from here, something like this, so that every alternate symbol is going with the alternate antenna. Are you getting it?
Yes, sir. Now clear. Previously, I thought.
So that is the reason. So this becomes 1 cross 2. Now you can have different combination. You can see here 4 layer, 3 layer also you can transmit, 5 layer and 2 code word, 8 layer and 2 code word. So there are different permutation combination. I have only covered 2 layer, 1 code word, and 4 layer, 1 code word.
Yeah. Now got it, sir.
Okay.
Because of this, what we are achieving, data rate or
okay, so we are achieving now you are able to transmit 2 stream, right? So data rate will be better. Because less time you are able to transmit more data.
Understood. Okay, thank you. Thank you, sir.
Thank you. So, okay. Okay, so now let me move to the last part, which is, so what I have done, I have just created one example so that you can understand, let's say you want to do some MATLAB implementation of this entire chain, how you can do it. So there is something called 5G toolbox in MATLAB. This is an additional toolbox that you can install. What we have done, we have used this toolbox to create transmitter, channel, and the receiver part, and then tested the performance of this entire channel. So you can see here, there is something randomly we have generated the input bits. So this is all the transmitter part I'm explaining. So, and A is the block size that, if you remember, the initial transport block. Then we have the first operation where transport block CRC had been attached. So there is something called NRCRC encode. Then what we have done, we have used another function which basically takes this input and it segment into multiple segments, that code block segmentation. Then we have LDPC encoder. Now you see that the base graph information is passed here. Which base graph it has to use. Then whatever you have received, then we are doing some sort of rate matching in this 2 part. Then we have scrambling the data, modulated it, and done the layer mapping. So it becomes your symbol after the layer mapping. Then this is the part which basically adds some noise to this. So we are here, we are using AWGN model. Definitely you can use more practical models where you can do entire OFDM modulate. So we are not using OFDM, rather whatever symbols are there, we are transmitting using the AWGN model. You can use some channel and add some OFDM to it. Then we have receiver. So at the receiver, if you are using any OFDM, what you have to do? First, you have to demodulate. But since we are not doing any OFDM demodulation. Whatever symbols we have received, we are doing layer demapping. So layer mapping, you have to reverse that operation. Then modulation, you have to reverse that to demodulation. Then we have we are again generated that scrambling sequence and get the de-scrambled output. Then we have to rate recovery, like reverse of the rate matching. Then we have LDPC encoding. Now we are doing decoding. Then whatever we are getting into the code block desegmentation. Again, basically concatenating it. And then we are doing the CRC decoding. And this out will be the output. And if this TB error is 1, it will indicate whether CRC is passed or failed, whether you have received it correctly or not. So what we have done, we have directly fed that out and compare with the actual input. And we got this bit error rate curve where the value of A is chosen to be 10,000 bits, rate as 449 by 1024. We are not doing any retransmission, so that's why this RV is 0. Modulation value is QPSK, number of layers as 1. So there is a basically layer mapping is not happening. SNRDB, if you change that, it will work. That code will also work. SNRDB, we have changed scale from -2 to 2. And these are the few values which is used for that scrambling sequence generation, RNTI, NID, and Q. And we are getting this performance. So I hope if you want to do anything on MATLAB, definitely these toolbox will help you. You can use this different functions to create your own chain. And let's say you want to work on any specific part of that, you can try and focus on that particular part. So let's say you want to work on something LDPC encoder. So you can create your own new algorithm here and replace this function. This will work, and then you can try and compare your performance. So this is the way you can work on it. So far in this talk, we understood the detailed procedure of downlink data transmission in 5G system. This primary procedure primarily categorized into 2 parts: transport channel processing and physical channel processing. Transport channel processing is responsible to enable the data for error detection and correction. Physical channel processing is responsible for preparing it for MIMO-OFDM-based transmission. Lastly, we have also seen how 5G toolbox can be used to replicate the entire PDSCH chain. So this is all about this talk. So thank you, everyone. Any questions are welcome. If you want to reach me out, this is my website. This is my LinkedIn page. I also am available on my email and my office phone number. Any questions, you can ask.
Sir, the entire discussion for 3 hours was very extensive. Are we going to get the PPTs? Because few of the calculations are, because of the speed, I was unable to cope up. Are we going to get the PPTs?
I think recordings are provided. Yes, Madhukarji?
Okay.
Yes, yes. Recording will be available.
That could be enough, right?
This evening.
Anyway, you are getting the recordings. Everything will be there.
Okay, thank you, sir.
Thank you, sir. It was very nice.
Yeah.
Since we are from computer science background, it was quite difficult for us. We will go through once again to understand it clearly, sir. Thank you.
I can understand if you're having it for first time because it requires a lot of background knowledge.
Yes,
and
sir.
it's
Thank you, sir.
difficult to complete that in 3 hours. Everything from basic.
Yeah, I understand. Yes, sir.
So
I have one question. Can I?
Yeah, please.
Recently, when I am going through literature and implementation, OTFS is one of the waveform candidate for 6G. Can we use all these parameters and as a OTFS, as a candidate waveform, can we do some kind of simulations?
Of course you can do it. Of course you can do it. So whatever I have done, so basically OTFS will come replace the OFDM part, which anyway I have not used. So what you can do, whatever data stream you are generating, that has to be modulated using the OTFS waveform, and then you transmit. So OTFS will be helpful to basically to support the. I hope you are aware of delay Doppler domain, where like basically high mobile scenario. Those things can be addressed using probably OFDM may not be able to handle that. So OTFS can play a role there, but definitely you can use that because 160 will come. That is a long way. For now, you have to get to do some simulations so that you can establish if there is any gain you can see or the utility you can establish of OTFS.
Okay, sir. Good. Thank you.
Thank you.
If there is no question, we may conclude, sir.
Yeah, I think then we can conclude.
So it was a very engaging session, and I think a repeat revision of this session is required for all the participants. There will be recording available by this evening, and Ashok sir is busy in some review meeting, so he will be joining tomorrow. And
Madhukarji, can you do that recording with me also?
Yes.
Okay, thank you.
It will be shared to you, sir, also, sir. So a very nice session, and thank you very much, sir. And we really congratulate you and all the participants for this wonderful engagement. And thank you, sir. Thank you all.
Thank you.
So
Thank
you.
you.
Close the session.
Yeah.
Yes,
Thank you.
Okay.
Thank you, sir. Thank you very much.
Thank you
So
so
tomorrow,
much.
10 o'clock,
Thank you.
will
Thank
be
you.
there. Yes. Thank you, sir.
Tomorrow, వాళ్ళిద్దరికి come to camp adjust చేసుకోమన్నారా? Yes.
Yes, tomorrow will be a session from 10 o'clock. So please join. Okay.
Sir, the recordings are having low resolutions.
Sir, Madhukar sir, one small request. Hello.